HR analytics, also known as people analytics, is the collection and application of talent data to improve critical talent and business outcomes. HR analytics leader enable HR leader to develop data-driven insight to inform talent decision, improve workforce process, and promote a positive employee experience. Moreover, what is being covered here is an edtech company that wants to hire data scientists among people who have successfully passed some courses and then sign up for the training, and the company wants to cut down on the cost and time of categorization of candidate. So hold on tight as we dig deeper and build on this case study. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.
The topic for today's industry session would be to look at how to prepare data for machine learning algorithms, right? Now, you must have understood by now, whatever practice you have done on various algorithms during the program, it is very important that you clean the data properly, right? Without cleaning it, you will not get great results. And also, for every algorithm that you're building, the data preparation steps are different. So how do you look into those small things, right? So that you get a robust model and which is like a very accurate one. Yeah. So as a part of this, we'll take up a case study which is on HR analytics, wherein we are going to look at an extensive EDA. So what type of EDA we should do for every project whenever we have some data set to analyze? What are the things that we need to look for in a EDA, right? So we'll be looking at an extensive EDA today, along with something called data leakage, right? So we'll look at the concept of data leakage, what it means and how it can be resolved. Then cross-validation, building models using pipelines. This is one of the most important steps when it comes to building machine learning models. Right? And in practice, when you go ahead and start using it for your work, you might want to fit multiple models to the same data, right? And compare between the accuracy. So how do you automate that process, right? So that's something using pipelines. And finally, we'll compare the various models using different data balancing techniques that we have learned. So we'll start with data leakage first. Right? So the term data leakage means here that we are sharing some information between the train and test set. The purpose of doing a split between train and test is because we want to build or train the model on the training set and then validate on the test, which is serving as an unseen data, right? So that we get to know about the performance of the model that we can expect in future. But there are some steps that we have been doing so far without a knowledge that it is not actually the right way of building correct or robust models, right? Because they are leading to data leakage problems. For example, when you scale the data, if you're scaling it before the train and test split, we are sharing the information between all the observations, right? And then it takes into account that data leakage issues, right? Data leakage can cause you to create overly optimistic model, if not completely invalid. Scaling the data set is one of the steps. Imputing missing values is another. And then we always tune the model on only in the training set, not on the test set, right? So this is something that we don't do. But scaling and missing value treatment is something that, majorly we do before the split. And then after the split, we just take the train and test set, fit it to the model, do a prediction and validate if the model is working okay or not. So we'll look at the process slightly differently today, where we say, what is the process in which we should perform these steps? So I've given a small graph here, which will help you to understand how to prevent data leakage. So basically, whenever you are doing a train and test split, right? For the training set, because we are going to learn sklearn package to do most of the stuff. With sklearn, there are two things. One is a dot fit transform, and one is just transform. Right? So we do a fit transform on the data set, which means fit is the part where we calculate the parameters. Let's say we want to scale the data, right? In scaling, what are the parameters that we calculate? If we are doing a z-score, then mu and sigma, right? Those are the things that we need to convert a value into their z-score. On the other hand, if we are doing a min-max scaling, the parameters are the minimum and the maximum value, right? So fit is to calculate the parameters on a given set, and transform, as the name suggests, is to use those parameters to convert the values. So we will say a fit transform on training set and just a transform on test set. Right? Let's understand this a little better with the help of one example. So when I say I'm building a model for, let's say, a default loan prediction, I want to build a model which will help me to predict who will default in future. Right? And for that purpose, I build a model, deploy it in production. Now, who's the end user of the model? Let's say I give that model to the clerk of my bank so that every basic application that comes in gets screened first, and I, as a risk manager, only get relevant applications to screen further, right? So do I expect the clerk of a bank to run a Python code and to generate those predictions and send it over to the risk manager? Obviously not, right? What a clerk needs is a UI. UI means a web interface wherein they can punch in the detail, click a button, and that displays a result, eligible or not eligible, right? Something like that of solution. So what we are doing in that, we have already a model in place that is hosted somewhere on the cloud. And through the help of APIs, we are trying to test one observation at a time. Now imagine you have some variables, and this is how the data looks like, right? Some dummy data. I'm filling some values. Let's say this is the type of data we are dealing with. There are some observations and some variables. Now you build a model on top of this. Right? Let's say you scale the data while building the model. So the values that you see here are all scaled. And you need mean and standard deviation in order to scale the data. When I'm passing only one observation through it, let's say I'm passing just one observation through the model for testing. Do you think we really have a mean and standard deviation for only one observation? I cannot calculate a mean or standard deviation for just one observation. So if my model is built on a scale data and I'm passing a test set, which is actual values, you know what the results are going to be, right? Highly incorrect. The model will not give you the great results or good results because your model is expecting a scale data, but you're passing actual values to it. So this is what is known as data leakage, right? Because in future, we are not going to use the inputs that are there in the model. That is why, while splitting the data set, we say fit transform. We calculate the mean and standard deviation and scale the data and build the model. And then we just say transform, which means take the mean and standard deviation that we calculated from the training set and transform the unseen data based on it. So if I already know what is the mean and standard deviation of the data on which the model is fitted, I can even calculate z-score for a single observation. I can say this is mu and sigma, this is x. I can get the value x minus mu by sigma, right? And that same applies for missing values too. Let's say if there are some missing values in the data and I'm imputing them with the median. If tomorrow I get a single observation, how would I get a median on just one observation? It's not possible. So what do I fill in with? I cannot fill a single observation missing value with a mean or a median because I don't have any other observations to work with, right? So in those scenarios too, I can take the mean or median that was used to fit the training set and use that value here in case I get a missing value in the test set in future. Right? So missing value is something that is surprising for most of the people. How we are going to do it after splitting the data set, that's what we are going to look at today. Because generally we have been following a sequence of steps wherein we read the data, understand how many null values we have, and then we impute it with mean, median, or any other statistical techniques. Yeah. So this refers to data leakage. And one of the other measures which should be done on hypertuning the model is to use cross-validation on training set only. Right? We'll talk about cross-validation in a few minutes. And to prevent the data leakage, all of the steps that I mentioned, can be done using pipeline. Pipelines in sklearn model is a very efficient way of doing all of this thing, right, without any fuss. Moving on to building the pipelines. Now, just now we discussed what data leakage is, what problems it can cause, and how to solve those problems. So one of the solutions is to build pipelines. Now, pipelines, as you can see here, is nothing but a sequence of steps involved for fitting various models. Now, let's take a case of two models, or let's say three models, right? One is KNN and one is random forest, let's suppose. Now, for KNN, you need the data to be scaled, right? That's a requirement because it is a distance-based algorithm. For random forest, there is no such requirement. You don't need the data to be scaled. Now, if you are scaling the data after splitting, let's say I scale the train set, I'll have to use that same train set for both the models. I cannot do like two different train sets. That will be an additional exercise for me to build two different train sets and scale one, don't scale other. So pipelines helps you there. Pipelines is a sequence of steps that you mention within each node. For example, if I want to train a few models, what I can do is perform scaling, maybe do a PCA as well. If I have a huge number of observations, let's say I'm also trying to build a linear regression or a logistic regression to it, and there is some multicollinearity in the data, I can do a dimension reduction as a part of pipeline. So which means that for every model we are fitting, we are using the same data set, but a different sequence of steps for each model. So I'm saying for X model, do these two things before building it. For the Y model, do these additional two things before fitting the data. Right? So it's basically giving you an automated way of building models and also cross-validating it at the same time. Because cross-validation is also important to understand the performance of your model on various sets. How consistent is your model on unseen data, right? How much of variance you have in the accuracy measures. So you can do a fit transform on all the training set because we want to calculate the parameter and transform it, which means to change the values. And on the test set, we'll just do a transform. We will use the parameters calculated on the train set to transform the values on test. And finally, we will predict out of the last step in pipeline. Right? So there are a few steps that you can predefine for every algorithm that you want to fit. What are the steps that you want to apply to that specific algorithm only? Right? Application of pipelines is something that we'll look at when we go to the case study. But this is the concept, the overall concept related to it. Next is about k-fold cross-validation. Most of you already know k-fold cross-validation is where you divide the data into equal number of buckets, and those many times the models will be iterated. Right? So if I am doing let's say a 5-fold cross-validation, which means I'm dividing the data into 5 buckets, treating one bucket as a test, 4 bucket as train, I get a performance measure. In the second iteration, the test set changes. So the performance would change, and so on for the rest of the iterations. Because the test set is changing, we get different results. And the objective of doing cross-validation is to understand how the model is performing on different unseen data. Because with the test set, when we say train and test, we are just passing the same observations, right? So we don't really know if I pass another set of unseen data, what would be the performance. And that is why we do cross-validation, so that the data can be divided into multiple buckets and we understand how it behaves to different kind of unseen data that is available. And finally, the overall performance is an average of the performance of each of these iterations. So you can get to know about the variance in the model, like if the model is performing at 50%, 60%, 70%. So if you see a huge variance between all the folds, which means your model is not consistent. It has some issues. Maybe you'll have to go back to your data cleaning steps and do something in order to fit it better. K-fold cross-validation often helps us to avoid the bias and the variances in the data. Bias is the overall error, which is the misclassified cases, and variance is the error in sensitivity, which is false negatives. The final piece for the day, which is data balancing techniques. So how do we balance the data? Balancing the data means whenever you're doing a classification algorithm, you look at the distribution of the dependent variable. There might be 2 or more classes. you look at what percentage each of the class represented. Right? Theoretically, whichever class has the highest number of observation is known as the majority class. Class which has minimum number of observation, it is known as the minority class. Now for majority and minority, if the number of minority class is less than 10% of the overall data, let's take an example of 1000 observations, which is split into 800 and 200 observation. 800 of zeros, 200 of one. So this is a 80-20 split. 0 is the majority class, 1 is the minority class. Here the minority class is 20%, which means it is greater than 10%. So theoretically, this is called as a balanced data. But you have seen the results on classification algorithms. When the data does not have a proper balance, it is predominantly skewed towards the class which has highest number of observations to it. Even though it is not unbalanced, right, as per definition, but you will get a result where the accuracy will be very high towards 0 and your recall towards 1 will be very low. So it is always preferred that the data should be 50-50 before you do any classification algorithm, right? Be it a decision tree, be it a boosted tree, a logistic regression, KNN, LDA, whichever classification algorithm you want to do, always prefer to do it on a 50-50 balance. Right? And that's where data balancing techniques comes into picture. In order to avoid these situations, there are two things that we do. One is called undersampling, one is called oversampling. And as the figure represent, oversampling means you are increasing the number of minority classes to match the majority. So if I'm doing oversampling on this data set, I have 800 zeros, so I increase this 200 to 800. So the overall size of the data is now 1600 observations. So that the overall meaning of the data is not changing. So the overall statistical measures of the data is not changing. These are some artificially imputed data points just for balancing the data. That's oversampling. Undersampling is reducing the majority to match the minority. In this case, this 800 will be reduced down to 200. And the total number of observations will then be 400 in case of undersampling. As you see, undersampling is removing some existing information from the data set. That is why it is not one of the preferred way of data balancing, while oversampling is preferred mostly. And one of the techniques that helps us in oversampling of the data is known as SMOTE, which is synthetic minority oversampling technique. It generates some data points for the minority class so that it is equal to the majority class. So that's about some of the topics. Now we are going to do a case study based on whatever we have discussed so far. And the case study is about an edtech company wherein they want to hire some data scientists who have successfully passed some courses and they have signed up for training. You can relate it to Great Learning in a way. Great Learning is also an edtech company who generally hires a lot of talent and treat the pool of job seekers as yourself, wherein you are going through a program, signed up for a training, and then when you successfully complete the program, how likely you are to crack the job. Right? So as a company, I want to make sure that I spend limited amount of resources on identifying candidates who are really looking for a job. So if there are 1,000 people who are taking training from me, I don't want to contact all 1,000. First, I want to understand from the learner's perspective if they are interested in a job change or not. And then we'll prefer working on only with these people who are ready for a job change, right? So that will help me narrow down my search and also help some resources. Like I don't need to deploy more people. It will be fast, convenient for everyone. So we are going to use the same technique, like the same example, and with the help of one data set that we have, which is information related to the demographics of the student, the education level they have, the total work experience, and some of the other details, right, which is collected during their sign up and enrollment to the program. So let's quickly jump onto the Jupyter Notebook and see how we can perform all of this with the techniques that we discussed. So the data dictionary given is a couple of variables which involves the enrollee ID, which is kind of a unique ID for every individual. The city code. So it has been dummy coded already for us. not dummy coded, but you can say it has been anonymized, right? City code represents 1, 2, 3, 4, 5, 6 like that. Then you have the city development index. City development index is a number given by the UN based on some parameters like infrastructure, waste management, health, education, and these parameters are on a scale of 0 to 1, right? Where does that city lie? Higher the number, which means the developed city it is. Lower the number, which means it is underdeveloped or developed. Then you have the gender of the candidate, whether they have a relevant experience for the job, enrolled into any of the universities, what is their education level, what was the major discipline, experience, the size of the company they are working for, what type of company it is where they are currently working, what is the difference between the previous job and the current job, right? What is the tenure in their current job, you can say. What is the number of hours of training they have received in their current job? And finally, the target, which is 0 to say not looking for a job change, 1 looking for a job change. So using this information, we are going to build the model and see which of these variables will come in handy. So we'll read a couple of libraries to get started. For manipulation, NumPy, Pandas, Matplotlib, Seaborn for visualization, for building the models, getting the validity and accuracy and all is using sklearn, right? To build a pipeline specifically, we'll call from sklearn.pipeline, import the pipeline and make pipeline functions. And then some of the models that we want to fit, like logistic regression, decision tree, AdaBoost, gradient boost, random forest, and XGBoost. Yeah. So we start by importing all the libraries and read the data first. I'm creating a copy just in case I need it later. If you look at the head, this is how the data looks like. You have the unique ID of all the learners, the city ID, the city development index in between 0 to 1, higher the number, develop the city it is, gender, relevant experience, whether they are enrolled into any of the universities, what is the highest education level, the majors, the total experience they have, size of the company, type of company, the last job, what is the duration, the training hours, and finally the target, which is our dependent variable. Right? So the data has been read properly. Let's go ahead and do some basic exploration, starting with the dimensions first. So the data we have is almost 19,000 observations with 14 variables in total, out of which 13 you can say are independent variables, 1 is a dependent variable. Yeah, so it's a very big data. The structure of the data gives us an information about the data types, wherein we say out of 14 variables we have, 10 are categorical in nature, 2 floats and 2 integers, with the total number of observations as 19,158. And the non-null component here gives us an idea of missing values. So there are some variables which has so many missing values in it. Right? So let's go ahead and check how many missing values we have. So in terms of percentage, the type of company has about 32% of its data point missing. With company size 30%, gender 23%, major discipline 14%, and rest of the variables are within 5%, with some of the variables do not have any missing values in it. So what we have done to get this percentage is count the number of missing values divided by the total number of observations we have in the data. So from the info, as you can see here, that company type has the most number of missing values in it. Right? Out of 19,000 observations, there are only 13,000 available, which means about 6,000 observations are missing. So 6,000 upon 19,000 gives us about a 32%. So we'll look at how to impute these missing values once we split the data, right? We are not going to impute the missing values before the split to train and test because we want to avoid those data leakage issues. And also I'm going to show you how KNN imputer can help you impute categorical variables missing data, right? Because we have seen so far that KNN imputer helps you to impute missing values for numerical variables, but we can also use it for categorical variables in another way, right? We are going to look at that as well. So if you look at the number summary for the 4 numerical variables by default, enrollee ID is just a nominal variable. We can ignore this one. City development index, the mean says 82%, almost 83%, which means the data or the job seekers that we have is mostly coming from developed cities, right? With a median of 90% city development index. And the range starts from 44% and goes up to 95%. Right? As far as the training hours goes, an average is 65 hours of training that they have received in their current job, with a median of 47, which means the data is slightly skewed. Right? And for the target, which is the dependent variable, the average or the mean value says only a 0.25 rounded off, which means the data balance is about 75 to 25. So out of all the 19,000 job seekers we have, 25% of them are only looking for jobs. 75% of them are not looking for a job change right now. So we go ahead and drop this enrollee ID, which is the unique ID, because it's not going to be useful. It is just a unique value. So I drop it. Now let's look at the summary for a categorical variables too. Right? For city, there are 123 levels, with the most number of job seekers coming from city 103. Right? As far as gender goes, we have 3 genders, so maybe male, female, others, wherein the most number of job seekers are male. Right? In relevant experience, we have only 2 levels, which is relevant experience and do not have relevant experience. Enrolled university, there are 3. No enrollment, maybe 1 is enrollment, and we'll have to see what is the third level. Education level, there are 5. Major discipline, SCEM, science, technology, engineering, and maths. Experience, there are 22 unique levels, with the most number of people coming from more than 20 years of experience. Right? Majority of the people working for a company whose size is in between 50 to 99 employees, and they are private limited companies. And last new job is 1, which means majority of the job seekers have less than 1 year tenure in their current job. And there are 6 unique levels to it. Now, why we are doing this? Because we want to understand that if I want to convert these categorical variables to numbers, I'll have to do a label encoding or a dummy, right? Most preferred is dummy. But if I do a dummy on this, I'll end up creating so many variables, right? Approximately about 160, 170 variables. So how do we look at this? Right? So we'll take a look at it towards the later half. Let's go ahead and start our ED. As I said, we'll be doing an extensive ED to understand the data in and out, to identify a lot of patterns within it so that it helps us decide what type of models to fit. Right? So this is a function wherein we are going to plot a histogram and a box plot together for a given variable. Let's say for the city development index, right? We see a box plot. So there is only one outlier that we see on the lower side, and the distribution is mostly skewed on the upper side. And that is also what we saw in the describe function, right? When we're looking at the number summary. So most of the cities seems to be developed cities. But if I want to understand which one is this outlier, so what I do is filter the data only for city development index less than 0.45, because this outlier seems to be less than 0.45, right? So it gives me a result that it is related to city 33. So all the observations are related to the city 33. So these 15, 20 observations that we have for this particular city seems to be outliers, right? So this is one of the underdeveloped cities, we can say, where the development index is less than 0.5. So this gives us one unique insight. If we go ahead and look at the other numerical variables for the training hours, there are some individuals who've got a very high training hours, but mostly people are in and around 50 hours. Right? So this data is slightly skewed. Now for the categorical variables, we want to do a count plot. Let's say for gender, we saw 3 genders. So male, female, and others. 69% of them are males, which is heavily skewed. Right? Then you have relevant experience. 72% of the candidates have relevant experience, whether they are enrolled into a university. So no enrollment, part-time and full-time. Currently, they are not enrolled to any of the universities, 72% of the candidates. Education level. So you have multiple levels starting from a primary school, high school, graduate, masters, and PhD, with most of the folks are coming from graduate level, followed by masters. Right? So this is kind of a univariate analysis that we are doing in order to understand the impact of each of those independent variables. Right? When it comes to major discipline, most of the people are coming from science and technology background. Company size. So for their current job, most of the people are working wherein the number of employees in the company is in between 50 to 100, followed by 100 to 500. Type of company, mostly are working with a private limited company, followed by a startup and then a public sector. For the last new job, so 1 or less than 1 year is the highest contribution. Then you have more than 4 years in the current job, 17% people. Now these will be looking for jobs predominantly, right? When we go to bivariate analysis, we'll compare it against the job seeker target variable 0 or 1. We'll see that most of the people might be here because they've spent a lot of time already in the current organization and now they might be looking for a change. Or maybe they've never worked before, they are freshers, right? And they are just looking to start their career. So these two probably will have the highest number of job seekers in it. Let's move on to bivariate analysis. So starting off with the correlation matrix. So we see correlation is not really impacting any of the variables here. There is not much of correlation. The highest we see is 34%, which is negative correlation between city index and target, which means that if the city is developed, then probably I'm not looking for a job being a candidate from that city. Right? So it's a negative relationship. Apart from that, everything looks okay. No problem, multicollinearity. So we go ahead and replace the target from 1 to yes and 0 to no in order to do our EDA further. And now we are going to compare the target variable with all the independent variables to understand its impact. Starting off with the city, we can see here a crosstab of the city, wherein it is also going to give us a plot to understand from which city most of the job seekers are coming from. Right? So this is sorted in a descending order of yes, which means the person is looking for a job. We can see city 171 has the highest concentration, where 100% of the candidates coming from this city are looking for a job, followed by city 139, 135, and so on. There are also a couple of cities where no one is looking for a job change. They're all satisfied and they're learning maybe just because they want to understand new technologies. So this is a good insight to have. Maybe I can filter my search on these cities only and exclude others, wherein I can get maximum number of candidates who are interested in switching to a new job. Then if you look at the comparison with gender, there's not much of a difference. As we can see here, it is almost 30% in all the three buckets, where male is slightly less. Females are the highest, followed by others. Right? 30% of the candidates who are females are looking for a job, almost the same for others. For males, it is slightly higher than 20%, maybe 20-25%. So we can say from this that maybe gender is not going to be a significant variable for predicting the target, because we don't see a difference between all the levels. So it's all the same. This is not going to help us predict if someone's looking for a job or not. Yeah. So let's say if we replace all the missing values 2 with unknowns, and then we do a gender split. So you see, for the unknowns, we have the highest, which means wherever we have a missing value in gender, they are mostly explaining if someone's looking for a job or not. So missing value treatment will be very important in this case. Yeah. If you plot the target variable against relevant experience, so those who do not have a relevant experience are looking for a job more than those who has a relevant experience. Right? Now, this could be because those who do not have a relevant experience, they're trying to learn something new and then they want to transition to that new field, what they have learned, right? Just like us. So most of the people who are looking for a job comes from no relevant experience background, and makes sense. Enrolled into university, those who have spent a full-time course in the university are majorly looking for a job change. Those who are currently enrolled into a full-time course, maximum distributions are coming from the full-time courses. Education level, most of the job seekers are graduate, because graduate was contributing to majority of the job seekers. So understandably, it has skewed the result for target as well, where the other levels are almost the same, right, if not different. Major discipline. Again, similarly like gender, there is not much of distinction we can see, but most of the job seekers are from these three categories, right, where it's science, technology, business degrees, and others. Minimum from arts. For experience, those who have less than 1 year of experience or just 1 year, they are the most interested in changing jobs, right? And overall, we can see most of the job seekers are less than 10 years experience. If you have more than 10 years of experience, then probably I'm not interested in switching the job immediately, because I'm already stable somewhere, and then I want to use the new learning, use the new skills in my existing work rather than shifting to a new field altogether. Okay. So people who are less than 10 years of experience, maybe we can say they are in their early stage of their careers and they're trying to build a name for themselves, and they learn new skills, so they want to show it, and by switching it to a different domain or different company. The ones who are already established, who have lots of experience, senior professionals, they want to use these skills in order to improve their own workflows. Yeah. Company size. Now, most of the job seekers are coming from company whose strength is between 10 to 49. And for the rest of the levels, it's almost the same. So it's again one of the non-significant variables we can say, wherein we don't see much of differences. The type of company, same thing, right? Not very significant. Last new job. See, this is what we identified during the first phase of EDA, that those who have never worked are more interested in getting a job in whatever skills they have learned, or whose tenure is just 1 year in the current company, they are looking for switch. Those who are stable, those who have more than 4 years, it's less likely they are going to switch. Right? We continue it to multivariate analysis, wherein we are trying to understand about training hours. So this is the distribution of training hours for those who are not looking for a job and those who are looking for a job, right? You can see here it's almost the same, not very big difference. And this is a box plot. Those who are not looking for a job, the box plot of training hours, whether there is no difference, as we can see. Those who are looking for a job, then we see a same split, but then we between the categories we see slightly difference. For city development index, see, for those who are not looking for a job, it's highly skewed towards the developed cities. For those who are looking for a job, we also have some distributions towards the developing cities as well. So this is one of the significant indicators we can say, wherein people who are looking for a job comes from developing cities too. From the developing cities, mostly people are looking for a job, and those who are not looking for a job mostly are coming from developed cities, right? And this is in the form of box plot. We see a clear difference. So this could be one of the significant predictors. Now, coming to feature engineering, I talked about creating dummy variables for so many new variables. Like you have city, where there are 123 different cities, right? So in such scenarios, instead of dummy coding all the levels, we always try to reduce the information. Let's say information is given in the form of countries. What is the high level information about a country? I can group them into continents. So if I have, let's say, 200 countries, I can group them into 7 continents, right? So that's reducing the information. If you have name of a car, maybe I can group them to brands. So if I have 100 models from different brands, I can group them into 5 or 6 brands. Similarly, for this city at the moment, we are going to group it using development index. Right? If you look at the number of unique levels in the city, there are 123. For each city, there is a development index. So based on the quantiles, I'm going to call them as underdeveloped, developing, or developed cities. Right? So from 123, I'm going to drop it down to just 3 levels. And I'm using the qcut function, which is the quantile cut, to create those buckets. So the first 25th percentile from the minimum development index till the 25th percentile, I'm going to call them as underdeveloped. From 25th to 50th percentile, from Q1 to Q2, I'm going to call them as developing, and Q2 and above, we'll call them as developed cities. Right? Now, if you look at the value counts for the city, out of those 19,000 cities we have, it has been divided into 3 buckets. 9,561 observation goes to developed cities, 4,800 to underdeveloped, 4,800 almost to developed. So 123 levels has been reduced to 3 levels. And this is the form of data reduction we should always do when it comes to machine learning algorithms, right? Because there are some limitations also in terms of creating dummy variables. This is generally known as the curse of high dimensionality. If you increase the number of variables in your model, not only it will increase the processing time, but also it will lead to overfit results, because more the number of dimensions, the higher the problem of multicollinearity in the data. So you do not want to increase the number of variables, otherwise you'll have to do a PCA or you have to do data cleaning further, right? Which is not required. You can try and reduce that information as much as possible within the category itself. And then once finalized, you can go ahead and create dummy variables for it. Now, coming to the missing value treatment and outliers. Right? So we are not going to treat outliers here because there are not much. We saw only one outlier when it comes to city development index. For training hours, there were few, but we can still live with it because we are going to build decision trees where outliers will not have that much of impact. So what we are going to do next is about missing value treatment. So for missing value treatment, as I said, we are going to use KNN imputer in order to deal with all these missing values for both the numbers and categories. For numbers, it is a simple distance calculation based on Euclidean distance. For categories, we are going to label code them first. Right? Based on that label coding, we are going to convert them into numbers, do a missing value treatment, and then reverse map for category. Right? Let's see how it is done. So if you look at the total number of missing values in the data, there are a couple of missing values, right, which you are going to impute. So we are going to create an instance of KNN imputer with 5 nearest neighbors. These are the variables that we are going to impute for the missing values. Right? So this is the data set, like a small subset of all the variables that we are going to impute missing values for. I'm creating a copy of the data just in case I need it later on. Right? This is how we are label encoding all the categorical variables. So we are saying a gender object where male is the existing value and we are going to convert it to 0. Female is an existing value where we are going to convert it to 1 and then others to 2. And using the map function, we are going to say that on the gender of the data, map it as per these values. So this is a dictionary, as you can see, key value pair. Wherever there is a male, replace it with 0. Wherever there is a female, replace it with 1 and others as 2. And we do the same thing for all the categorical variables one by one. So this is a one-time activity. If you don't want to impute missing values using KNN for categorical variables, I do not recommend you do it using mode. Right? Mode is preferred by most of the people, but instead of mode, say all of them as unknown, that you don't know what the value is. Right? That's one of the other preferred way of imputing missing values for categories. But as much as possible, try and use this way. If there are a lot of categorical variables, then you can probably say unknown. That wherever there is a missing value, replace it with an unknown, a unique level itself. But don't use mode, because the distribution of a categorical variable might be highly skewed. And if you're using mode, you're skewing it further, making it irrelevant for the dependent variable. Right? So I'm going to show you a different technique today, which is to first label code the categories and then use these numbers to run a KNN algorithm and reverse map it. So let me run this. Label encode. Now, if you look at the data, we have all these variables, which was string earlier. We've imputed them to number. Right? Now, the ones that you see here do not have any missing values, so it's okay, right? We are only going to impute missing values for the columns which are already in numbers here. So first of all, we go ahead and split the data, just like we do for any machine learning algorithm. Convert it to X and Y, which is a list of independent variables and the dependent variable. Because we converted target into yes and no, so I'm converting it back to ones and zeros. By using a lambda function, we say wherever it is yes, convert it to a 1, otherwise a 0. And then from the X and Y, we split it into 70-30 ratio to call it as a train and test split. So we have about 13,500 observations in train and 5,700 observations in test. Now, to avoid those data leakage issues, we are going to only impute missing values on training set and then transform it to the test set. So we say from the training set, on the columns that were required for missing value imputation, do a fit transform of KNN. Right? So which means that for the training set only, fit the KNN model and impute all the missing values in train. But for the test set, we are saying just transform, that whatever distances we calculate for the training set, use those distances to impute the values in the train set too, test set too. This is going to take a couple of minutes because the number of observations is very high. Now, once this is done, if you look at the number of missing values, it will say 0 for both. Right? While this is running, let me explain the next set of code. This is for the inverse mapping. Inverse mapping of these categories, because we coded them as numbers. Now I'm going to reverse map it. Right? So for 0, I'm going to call it as male. For 1, I'm going to call it as female, and 2 for others. Because we have done the missing value imputation, so we can go ahead and do the reverse mapping. You can see all the missing values have been imputed for both the train and the test set. So we are good to go there. For the inverse mapping, we are going to use the same dictionary that we created earlier, and we are going to map it as inverse and apply it to all the variables one by one. So if you look at the value underscore count for each of the categorical variables in train now, you have the city, developed, underdeveloped, developing. See, gender is again coded as characters, relevant experience, enrollment status, the education level, the discipline, the total experience, the size of the company, type of company, and the tenure in the current job. So everything has been encoded, reverse encoded, right, from number back to their original class. And the same for test. So you can see the distribution of all the levels in the category. So this is one step of avoiding data leakage, wherein we are imputing missing values after the split. We are doing a fit transform on the training set and just saying a transform on the test set, so that we can leverage the distances that we calculated in training set to impute missing values in the test set too. Yeah. And we are going to get dummies for all the categorical variables. Now we reduce city, so we do not have many levels remaining. There are about 15 to 20 levels that are there. So we drop the first level and get the dummies for each of the categorical variable in both the train and test set. So the number of variables now in our data is 56 in total, with the same number of observation, 13,410, 5,748. So this is completes your data processing steps, data cleaning steps, wherein we looked at a lot of things, did an extensive EDA to find out which variable might be a better fit, or which can explain a higher amount of variance in the dependent variable, which are closely related, right? That gave us a lot of insight during the EDA phase. Now we will put those insights into machine learning models and build pipelines. Now, while dealing with classification, there are two things that we always focus on. The first thing is a false positive, and the other one is false negative. Depending case to case, we try to optimize one of those two, right? Either we try to increase the recall or increase the precision. Now, generally, how do we interpret a classification or a confusion matrix, right? Let's say I did some campaigns, right, for a marketing campaign on 1,000 customers. Out of those 1,000 customers, I spent about $10 in contacting each of the customers. So what is the total amount I spent? About $10,000, right? And the outcome was that out of 1,000, there were only 100 customers that applied for a loan, right? Let's suppose this campaign was to ask users to apply for a loan, giving them some preferential rates, right? So only 100 people applied for it. So what was the conversion rate that I got? Only 10% by spending $10,000 on the campaign. Now assume I take the same 1,000 observations where I know what is the outcome, right? I'm trying to run a second marketing campaign next year. But this time, I do not want to go with all the customers. I want to use the previous experience I had, build a model, and then proceed with the campaigning. So I decided to build a model on these 1,000 observations where there was 100 yes, 900 no's to predict on a data set. Let's say we have 1,000 customers again. So we have zeros and ones. This is actual. Let's say this is predicted values. And out of 1,000 customers, I'm predicting that, on this model that we built, we are saying that 900 customers did not apply. So out of 900, we have, let's say 850 here, 50 here. And out of 100, we've got, let's say 70-30. Or let's say 50-50. Right? So in this case, my overall accuracy is around 900 upon 1,000, 90% accurate model, but the sensitivity is just 50% and the precision also is 50%. Right? Now, how can I read this confusion matrix back to the business? I'm saying instead of contacting 1,000 customers, I can only contact the 100 customers my model is saying they are going to apply for a loan. If I'm going to contact these 1,000 customers only, my budget will be $1,000. So I've got a cost saving that I was able to save $9,000. What is the conversion rate? 50%, better than before. So I can spend the rest of the resources in gathering more customers' data and put it to the model and contacting them. I'm eliminating all those customers who do not have a high probability of applying for a loan. And I'm only focusing on wherever there is a high probability. So this is how you need to interpret this confusion matrix. And depending upon scenario, you might want to reduce this 50, which is your false positives or false negatives. In our case, we have these two same thing. Predicting an enrollee looking for a job, but in reality, the enrollee is not looking for a job. This is loss of resource. We are unnecessarily spending time on these applicants, right? These are false positives. Enrollee is not looking for a job, but enrollee is looking for a job. So we are predicting that someone is not looking, but in actual, they were looking for a job. This is loss of opportunity. Right? So we want to reduce the false negatives as much as we can. And reducing the false negative means we want to get a higher recall score. Right? So we get started by building the pipelines. This is how we build a pipeline. So I define an empty list of models, all the models that I'm going to fit, and then say, what are the different models? So because this is an empty list, I can append to it. This works in the same fashion as dictionary works. You have a name and a value. So key value pair, you can say. So logistic regression is the name. And what is the value? Value is the pipeline I'm going to create. Within the pipeline, what are the steps I want to take? So first of all, I want to scale the dataset using standard scaler. And then logistic regression, which means I'm going to build a logistic regression model on top of the scale data. So see here, when I converted it into train and test X and Y, I did not scale it. I'm scaling it during the pipeline, which is right before fitting the model, scale the data. Now, if I'm building those scenarios of KNN and random forest that I explained before, where KNN requires scaling and random forest does not require scaling, I can fit it into this pipeline step. I can say step of standard scaler for KNN model, and I can exclude it for random forest. If I do it standard for all the algorithms, if I do it on the train and test set here on the top, then I'll have to use it for every model, right? Which might not be required. So that's why pipeline. So we are going to do a scaling and a model fitting for all the type of models. This is just to explain how pipeline works, right? You can do a PCA too in case you need it. So you use a pipeline for random forest, logistic regression, building a gradient boosting model, add a boost, XGBoost, and a decision tree. So you can see we are doing append, which means we are adding it to the list. Finally, if I run this algorithm, you see what we are doing is by running a loop, iterating through each of the key value pair on the basis of recall and a cross validation based on 5-fold, we are building those models. And it is printing out the average of all the cross validation scores, right? On 5-fold cross validation, what is the result? So for logistic regression, we got an average recall of 30%, random forest 37, gradient boosting of 42, ADA boost 34, XGBoost is 41, and the decision tree is 39. So the highest that we were able to achieve was in boosting techniques, which is gradient boosting and extreme gradient boosting. If you look at the consistency of all the models, so I can draw a box plot that for logistic regression, out of the 5-fold cross validation we did, the validation scores were from 29% to close to 30%, with gradient boosting with the highest median of 43% approx, and extreme gradient boosting is approximately 42%. So for XGB and GBM, you see there is a huge variance. Right? From 38%, the performance is up to 45%. But for the other models, it is quite consistent. Yeah. Now this recall is very low. This is not acceptable when it comes to real life applications. If you have a recall of 40% only, that's as good as not having a model. Right? So what we do is balance the data, because the data was skewed towards one of the class. There was a 75-25% split. So I'm trying to do oversampling using SMOTE. Oversampling is increasing the number of minority classes. Okay, I did not import the library, sorry. So if you look at the sampling result, before the split, the result was this, that in the training set, there were 3,300 observations for yes, and only 10,066 for no. Now, because oversampling means we are increasing the number of minority to match the majority. The majority remains the same, but the minority class has been increased to match the majority. So instead of about 13,000 observations, we are now going to build a model on 20,000 observations. Right? And I fit the same pipeline to the oversampling data. And you can immediately see the results are far better than what we got with the original split. The original split was around 30 to 40, right? In between 30 to 40 mostly. But after oversampling, the result is in between 75 to 80%, or even more than 82% for some algorithms. So we've got a very high recall once we have oversampled the data, which means whenever we balance the data, you can see the result. We did not change anything in the data preparation step. We just balanced the data set to 50-50. From a skewed result, we got a balanced result now. And the highest accuracy that we see is across random forest and extreme gradient boosting, which is 82% recall. And that's a very good recall to have. Right? Even for a random forest, the model performance is consistent, you can see, with respect to gradient boosting, where you see a huge variance in all the cross validations. So the number has improved drastically. Let's also try undersampling. So from the same IMB learn, we import the undersampling and a random undersampler because we want to reduce the number of majority. So randomly, we want to keep some observations to match the minority. So you see, we have reduced the majority to match the minority. So instead of 13,000 observations, we now have about 6,700 observations to work with. And I go ahead and fit the same pipeline to it. So to see the result, it is still better than the original split of 75-25, but not as good as oversampling results. But most of the models show a less variance in it now. You see, many models are at the same level. With oversampling, there was a difference between all the models, stating that for each one of them, the model performance is not the same. But with undersampling, it's almost the same. So you can either go with oversampling or undersampling, because in both the cases, you've got some valid results. So this explains how you are going to fit data a better way, avoid data leakage issues by imputing and scaling after the split, right? And how do you fit multiple models at once by building pipelines and compare the cross-validation results as well. Now, if you want to take any of these algorithms, let's say I want to consider random forest out of this as my final model. So what I can do is, if from this pipeline, I only want to get random forest, the object was models. So if I look at models, you have all those models within a list. What is the index for, let's say, gradient boosting? So this is 0, 1, 2, 3, 4. If I say, give me the fourth element from this list, it returns the XGBoost model. Now within this XGBoost, there are two items. One is the name, second is the pipeline. So I can only use the pipeline to predict the data, right? So I can say, return the first element. This is the XGBoost model. I can take it now, predict on the test set, use the prediction to build a confusion matrix, a classification report, and then take it forward. Yeah. So you fit many algorithms at once from a pipeline. Once you identify or freeze down on one of the models, fetch those models from the pipeline and use it further. Maybe I can just name it as XGBoost. And then use XGBoost as the model. Say XGBoost.predict on the test set. And anything that I want to do further with this model. So this completes the case study.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.